All right, let's talk about the elephant in the room when it comes to artificial intelligence, the math. Today, we're diving into a fascinating explainer that tackles what is often the biggest roadblock for people getting into this field. But the source material offers a really refreshing perspective shift. Instead of panicking over complex equations, just think of math simply as a language. It's really just the specific vocabulary and grammar we use to talk to machines. So let's jump right in and learn how to speak it.
The source material has this absolutely great quote that I think hits the nail on the head. Let's start by revisiting the mathematical notation we all learned at school, but some likely forgot right after the prom. It's just so relatable. If you get a headache looking at dense mathematical symbols, hey, this explainer completely validates that. We're going to wipe the slate clean today and literally rebuild this language step by step so it makes perfect sense. So here's our roadmap for this explainer. First up, essential mathematical notation. Second, functions, derivatives, and gradients. Third, probability and random variables. And finally, we'll wrap up with machine learning paradigms. Let's kick things off with Section 1, essential mathematical notation, or basically, building our alphabet. Before we can write full sentences, right, we need letters. And the absolute most basic letter in our machine learning alphabet is the scalar. A scalar is simply a single numerical value. It could be 15, it could be negative 3.25. When we write this down in math notation, we just denote a scalar using a simple italic letter, like X or A. It truly doesn't get simpler than this, just a single standalone number. Now, what happens if you group several of those single numbers together? Well, you get a vector. Think of a vector as an ordered list of scalar values. We call these individual values attributes. And to show we're talking about a vector and not just a single scalar, we use a bold character, like a bold X or W. The absolutely crucial thing to remember here is the order. Changing the sequence of the numbers changes the vector entirely. To really visualize what a vector is, think of arrows pointing in very specific directions, or even individual dots floating in a multidimensional space. For instance, a vector with the values 2 and 3 can be thought of as an arrow moving exactly 2 units horizontally and 3 units vertically. Or it's just a single dot sitting right at that exact coordinate. So vectors are super strict about order. But what if we just have a bunch of unique items, and honestly, we don't care about the order at all? That is called a set. A set is simply an unordered collection of unique elements. We usually denote a set with a fancy calligraphic capital letter like an S. It's kind of like a bag of unique items. It really doesn't matter what order you pull things out of the bag because it's still the exact same bag. Okay, brace yourself, because here's a symbol that usually makes people want to run for the hills. The capital sigma. It looks like a giant, intimidating, jagged E. But here is the secret to demystifying this jargon. All it means is add these things together. That's it. It just denotes the summation over a collection of elements. Whenever you see this spiky symbol in an ML paper, just tell yourself, okay, the machine is just doing a bunch of addition right here. And right alongside sigma is its sister symbol, the capital pi. If sigma means add, pi simply means multiply. It denotes a product of elements in a collection or the attributes of a vector. So if sigma is your big addition loop, pi is literally just a big multiplication loop. See? Not so scary. We're just combining our basic alphabet into simple words now. Let's look at how all these vectors actually interact. You can add or subtract vectors and boom, the result is just another vector. But check out the dot product. When you calculate the dot product of two vectors, it actually squishes them down and the result is a single scalar, just one number. And that transpose operation? That's really just flipping a vector on its side, taking a vertical column of numbers and turning it into a flat row. Moving right along to Section 2, functions, derivatives, and gradients. Basically, the grammar of change. If scalars and vectors are our nouns, then derivatives are absolutely our verbs. In machine learning, we are completely obsessed with how things change. And that leads us straight to the derivative. A derivative is just a way to describe how fast a function is growing or decreasing. It measures the speed and the direction of that change. Positive derivative, the function is going up. Negative, it's going down. This concept of change is so crucial because in machine learning, we are almost always hunting for the lowest possible error. We are looking for these specific valleys, known as local or global minima. When a derivative drops to exactly 0, it means the slope is perfectly horizontal, which acts like a giant flashing sign telling our algorithms, hey, you've successfully reached the bottom of the curve. But the
the source points out a major catch here. A standard simple derivative only works if we're dealing with one single input variable. And real-world machine learning models, they have hundreds, thousands, sometimes billions of inputs. So we have to upgrade our derivative into a gradient. A gradient is basically a supervector made up of many partial derivatives. It lets us track all the moving parts and find the direction of change across multiple dimensions all at once.
All right, Section 3, Probability and Random Variables, how we navigate the real world. Because let's face it, the real world is messy. It's not a neat, perfectly predictable math equation. To capture all that real-world uncertainty, we use a random variable. This is a variable where the possible values are just the outcomes of a random phenomenon. And we split these into two camps. Discrete random variables are for things you can clearly count, like picking a color, red, yellow, or blue. Continuous random variables are for things that can take on an infinite number of possible values, like measuring someone's exact height or weight. When we map out the probabilities of these variables, they look quite different. For discrete, countable things, we use a probability mass function, which maps out distinct categories and looks kind of blocky. But for continuous, infinite things, we use a probability density function. It forms a smooth, continuous curve, and mathematically, the total area underneath that curve always equals exactly 1. So, how do machines actually use these probabilities to learn anything? Enter Bayes' rule. This is, without a doubt, one of the most vital concepts in all of statistical learning. Bayes' rule gives us the exact mathematical framework to update our model's parameters and beliefs the moment we feed it new data. It's the literal engine of learning, constantly adjusting conditional probabilities as fresh evidence rolls in. And finally, Section 4, Machine Learning Paradigms. It's time to write some sentences. This is where all the pieces come together to form full ideas. Let's look at the major problem types the source highlights, starting with classification versus regression. Classification is all about assigning a specific category or label to something, like an algorithm scanning an email and definitively tagging it as spam or not spam. Regression, on the other hand, is about predicting a real valued number, like guessing the exact dollar price of a house based on its square footage. So it basically boils down to labels versus numbers. Then there's the question of how these algorithms actually remember what they've learned. Here we have model-based versus instance-based learning. Interestingly, the source points out that most algorithms are model-based. They look at the training data, learn the mathematical parameters, the variables and gradients we just talked about, and then they completely discard the original data. But instance-based learning, like the K-nearest neighbors algorithm, doesn't throw anything away. It literally uses the entire training dataset itself as the ongoing model. And finally, we have the architecture of the learning itself, shallow versus deep learning. A shallow learning algorithm learns its parameters directly straight from the features of the training examples. Deep learning, however, takes this to a totally different level, using complex neural networks with multiple layers stacked up between the input and the output. In deep learning, the parameters are learned from the outputs of the preceding layers, which creates an incredibly nuanced, deep understanding of the data. And that wraps up our explainer. You officially have the mathematical vocabulary down. The scalars, the vectors, the gradients, the probabilities, the entire foundation that makes up the language of artificial intelligence. You know the alphabet. So, the provocative thought the source leaves us with is this. Knowing what you know now, will you start by building shallow, interpretable models? Or are you ready to take this new language and dive deep into neural networks?